started. We're very honored today to have our seminar speaker, Dr. Wayne Lee from the Jet Propulsion Laboratory down in Pasadena, California. Dr. Lee got his bachelor's degree at UC Berkeley and then got his PhD at the University of Texas? University of Texas in Austin, and then went on to work at several different locations within NASA centers. He worked at Johnson, he's worked at the Jet Propulsion Laboratory. Today he's going to talk to you about his work when he was at JPL with regard to the Mars exploration rovers landing and some of the engineering and science that went into landing rovers on Mars. So Dr. Lee.
All right, so thanks for having me here. Today come to talk to you about a project that we worked on about 10 years ago called the Mars Exploration Rovers. There's probably no more of a bigger challenge we have in spaceflight than landing something on another planet. It's something that's really hard to do, primarily because when we send some stuff to other planets, we don't have pilots on board to guide the spacecraft to a safe landing on the surface. So we have to rely all on autonomous instruments and the fact that we really understand our physics correctly. So the reason this talk is entitled 6 Minutes of Terror, because that was a phrase that was coined by our Mars program manager about 10 years ago, because 6 minutes is about the amount of time it takes to get from the top of the Martian atmosphere all the way down to the ground. And in that time period, the spacecraft is usually on autopilot, and there's not a thing that you can do on the ground to help it out. You got to pray that you did your work correctly. So let's talk a little bit about Mars and why we want to explore Mars. This is a photograph which I've cut out of the Earth and Mars, if we could place them side by side. As you can see in this photograph here, that this composite, Mars is about half the size of the Earth in terms of diameter. And the interesting thing, though, is that Mars has a lot of land to explore, because unlike the Earth, there are no oceans covering the Martian surface today. There may have been billions of years ago. So because most of the land on the Earth is covered by oceans, Mars actually has as much dry surface area as the Earth. So in terms of dry land on the Earth. So when you look at surface to explore on Earth and surface to explore on Mars, they're about equivalent. The other interesting thing about Mars is that it has about 38% of the gravity on the Earth. So that means if you weighed 100 pounds on the Earth, you'd weigh about 38 pounds on Mars, which is a great idea if you're into weight loss. But primarily, the reason that we explore Mars is that Mars is perhaps the only planet in the solar system that has a climate very similar to Earth in terms of temperature. Now, when I say very similar, it's not like it's here in like Seattle or even here in Canada or anywhere in the United States. The average surface temperature on Mars might be like 120, 130 degrees below zero. So a warm day on Mars would be like, a warm day on Mars would kind of be like what it is in Antarctica on a regular basis. But compared to the rest of the solar system, that's actually pretty warm. Also, a long time ago in Martian history, we believe that there was a lot of water on Mars. The water on Mars today is mostly locked up in the polar ice caps. Some of it may be frozen beneath the ground. But it's because Mars used to have water that we believe that Mars may have been an oasis of life a long time ago in the past. We don't know if there's life on Mars today. If there is, certainly it's not wild animals like hippos and giraffes wandering around. We would have seen them already. But it's probably bacteria that's buried in the soil somewhere, or microbes. So we don't know if Mars has life today, but we believe that the conditions on Mars 1 billion or 2 billion years ago in the past may have been hospitable for the development of life. And that is one of the reasons that we keep exploring Mars, is to find out if this is true. So our mission that we launched in the June of 2003, so almost 10 years ago, it's called the Mars Exploration Rovers, the acronym was MER, so it stood for Mars Exploration Rovers. And so the caption of this slide here is "Win or Go Home." And let me tell you, the phrase "win or go home," for those of you that are basketball fans, since this is basketball playoff time, and you know your old Seattle Supersonics, which aren't in town anymore, now deep in the NBA playoffs. It's a coined phrase from the NBA playoffs where you got to win your next game or your season's over. And this is literally what the environment was like at NASA in 2003. So let's see, most of you are what, about 20, 21 years old. So you would have been 9 or 10 at the time. But if you'd remembered what had happened back in the early 2000s, we had a series of unfortunate mishaps, shall we say. In 1999, we were sending 2 spacecraft on their way to Mars, the Mars Climate Orbiter and the Mars Polar Lander, both of which didn't make it to Mars for various reasons that we won't go into here today. It's a story for another day. And then in, I'm trying to remember this correctly, February of, that would have been 2003, we lost Space Shuttle Columbia upon reentry into the Earth's atmosphere. And so here we were in June of 2003, having launched the Mars Exploration Rovers, and we were going to land them in January 2004. It was literally do or die time, based on the loss of the Mars missions in 1999 and the loss of Columbia in 2003. A lot of high-profile things were going wrong, didn't work, and the Mars Exploration Rovers were our next high-profile mission. So literally, we were sitting there thinking, if this didn't work, boy, that would be the whole space program going down the tubes. A lot of what we do out there, even though it's very high risk, we've got to get it right, just because funding and public perception is so fickle. Even though it's very easy for these things not to work, because this is a very high-risk endeavor, the public still expects that all of these things actually wind up working, and that we spend the taxpayer dollars in an appropriate manner. So imagine this. This was the night of January 3rd, 2004. We had launched the rovers approximately 6 months ago, and we were waiting to see if they were going to land on Mars correctly. So there's my project manager, Pete Teisinger. It's Steve Squires, principal investigator of the science from Cornell University, and this guy here, Sean O'Keefe, who was the NASA administrator at the time. They're waiting for the signals to come back from the rovers after we landed. And there's me at the flight control console, my boss, Rob Manning, and communication engineer, Polly Esterbrook. We were sitting there waiting for the signals to come back from Mars as to whether we had actually touched down on the surface safely. And that was just a very long time. I think it was maybe 8:30 in the evening that we were sitting there. We had entered the Martian atmosphere 6 minutes earlier, and we'd gotten a little blip of a signal at about the time we were supposed to have touched down, but then nothing. So I was looking at my computer screen here, and the signal strength of the radio just showed blank. It was just all zeros going down the bottom of the screen. And we had no idea as to whether all zeros meant that, well, basically the rover was dead because it was smashed to a million pieces on the ground, or that the tracking antennas hadn't picked anything up yet. And so it's just in one of those times where I was just sitting there thinking, wow, looking back on 3 or 4 years of development. We had started this project back in I think it was March of the year 2000, wondering, okay, all the decisions that we had made over the last 3 years, trying to second guess every one of them. Well, did we do this right? Did we do this right? Should we have done that differently? And in reality, it was only a few minutes of time when we were waiting for that signal, but it just felt like a million years. And just one of those times you just sit there with knots in your stomach, wondering, boy, did we just really mess up in front of national TV? So let's go back a little bit to how we got to where we were on that night. This is a photograph of the Mars Exploration Rover in the assembly facility at the Jet Propulsion Lab in Pasadena, and this is just to give you an idea of size. This is the Sojourner Rover that we launched in 1996, and it landed on Mars on July 4th, 1997. And this was the very first rover that we ever sent to Mars. It was the size of a laser printer, and it couldn't do much other than it could drive around. It had some remote sensing device to try to measure the chemical composition of rocks, but it was not a very capable rover. It was more of an engineering demonstration that we could send a rover to Mars. Now this guy here, the Mars Exploration Rover, as you can see here, is about the size of a riding lawnmower, weighed about 400 kilograms, so that's about 800 pounds. And you can see here it has 6 wheels. There was a camera on top of a mast, and the camera had 2 eyes so that we could take stereoscopic pictures. And then in front, which is hard to see here, there was a little robotic arm. At the end of the robotic arm, there was various instruments. We had instruments that could sense what was inside rocks. We had a little drill that we could drill inside rocks, and we could take pictures of microscopic images of what was going on inside the rocks. And it was a very, very capable spacecraft in terms of scientific instruments. But here, I just want to give you the size of something like this. So the challenge that we faced was, how do we get something looking like this, weighing 800 pounds onto the surface of Mars without breaking it into a million pieces? So here's another image of the rover, and one of the hallmarks of the rover here is you can see that it has 6 wheels, and this is the wheels sat on these arms here, which is what we call Rockerbogie Suspension, which meant that the wheels on these arms could move up and down as the rover drove over rocks. So the rover could actually drive over rocks about twice the size of its wheels because of this Rockerbogie suspension. In reality, when we got to the surface of Mars, we never trusted the rover to do that, and anytime we saw rocks, we actually programmed the rover to drive around the rocks. But it was certainly capable of driving over rocks. And one of the challenges of getting this thing onto the surface of Mars, though, is it's an odd shape. And you can see here these wing-like projections on top. They're actually solar panels that provide the rover with electricity from which to drive. So, getting to Mars, how do we do that? Well, first of all, in the assembly room, you can't actually fit something like that inside the top of on the top of a rocket. Things have to, when you launch things into space, a rocket is very slender looking and has a nose cone at the top. So everything has to fit inside that little nose cone. So the first thing we did is that we designed the solar panels so that they folded up, like you see here in this picture. So in the previous image, you can see that that when unfolded, they made a wing-like projection, but whoops, going the wrong way here. But when we folded them up, they kind of made this little triangle shape. And then what we did here is that, if you notice, there's this platform that the rover sits on. You can see the wheels are also folded up as well. And this platform actually has 3 panels, panel 1, panel 2, panel 3, and the rover is sitting on the base panel. So now, the next step here was that this panel actually folded up, and so that you can see that the rover is encapsulated inside these 3 panels, and it's folded up almost like a pyramid, and this is what we call the Tetrahedron. And so now, this tetrahedron, when fully closed up, looks like a 4-sided pyramid. And then on the outside of this 4-sided pyramid, there are these airbags, which I'm going to explain to you what those airbags did in a little while. But you can see that rover, which had 6 wheels and solar panels that stuck out, was nicely tucked into this pyramid-shaped structure. And it's this pyramid-shaped structure which we actually didn't even put that inside the rocket. And I'm going to show you that in a minute. So, it gets even more complicated. Now, the rover's inside the tetrahedron here, and now what you see here is that we're lowering this thing called the back shell, and it's going to go over the rover that sits inside the tetrahedron. And the reason for the back shell, which we'll show in a minute here, is that the back shell is part of what protects the rover during its flight through the Martian atmosphere on its way from space down to the ground. And so once the back shell is on top of it, as you can see here, this was some of the launch technicians had an interesting sense of humor. So this is the back shell, and then this bottom part here is the heat shield, which we'll talk a little bit more about the heat shield in a minute. The heat shield goes, as you can see here, goes on the bottom, and so the tetrahedron that the rover sits in would be see me tracing out with a laser pointer, would be sitting inside the structure. So this whole thing that encapsulates the tetrahedron is a device that we call the Aeroshell, and it's this Aeroshell that protected the rover during its flight through the Martian atmosphere. And so what you see on top here is this is a device that we call the cruise stage. On the way to Mars, we have to have electricity to actually run the spacecraft. You remember the rover has solar panels, but because it's folded up inside this Aeroshell, solar panels don't get any electricity during the flight from Earth to Mars. And so there's solar panels on top of this cruise stage. And also this here is a fuel tank. We had to perform trajectory correction maneuvers on the way to Mars, and that contained the fuel to actually fine-tune the trajectory on the way from Earth to Mars. So it's this spacecraft here that we sent to Mars in order to get the rover safely down onto the ground. Now, so to show you what we did, I know that was kind of hard to follow. It makes sense to me because I had to live this every day. But you can see the rover is right here. You can see the 6 wheels. The blue is the solar panels that I was showing you before. Remember, the solar panels folded up. The solar panels the rover sat on this base panel, and then we had 3 pedals that folded up to form a pyramid that you see here. And then there is the back shell and the heat shield that come together to encapsulate the tetrahedron, and then we had the cruise stage that we put on top of it. So this was almost like the Russian dolls, where you have like a doll inside a doll inside a doll inside a doll, except for in this case it was almost like origami inside a doll inside a doll inside a doll. And so one of the things that I tell the recently graduated students that come work for me is that everything is the way it is for a reason. We just don't do complicated crap like this just to do something cool. And so in a minute here, I'm going to show you why it is we put something really complicated looking scheme together like this. And then in total, to give you an idea of size, the diameter of the Aeroshell was approximately 2.65 meters, which is about 10 feet. And the reason that it was 10 feet is that the diameter of the rocket, on top of the rocket in the nose cone, was about 10 feet. So we were unable to make this thing any wider. This is the largest that we could make the Aeroshell and still fit inside the rocket on the top, inside the nose cone. All right, so now that's just to give you an idea of what the spacecraft looked like going to Mars. So let's talk a little bit about the fun stuff in terms of getting to Mars and actually landing on the surface of Mars without smashing the thing to a million different pieces. So what this photograph here is that this is a photograph of a rocket called the Delta II. It was one of the mainstays of the United States rocket force ever since the 1960s. The Delta started off its life like in the late 50s as an ICBM in the days of the Cold War, where we had to have lots of missiles capable of lobbing nuclear warheads to Russia. So the Delta was originally one of those original ICBMs. This was the late 20th century version of the Delta rocket, and it stands about 35 meters tall, and most of this rocket is actually fuel. So you can see here at the bottom there are 9 helper rockets that we call solid rockets. A solid rocket is basically a rocket that the fuel is basically like this putty, and you ignite the putty and the putty burns. And so it has 9 of these little helper rockets to help the rocket get off the ground. It has a first stage, and it has a second stage, and then there's a third stage up here, and then here's the white nose cone is where the cruise stage and the Aeroshell sat, right up here at the top of the rocket. So the job of the 9 helper rockets is to help the rocket get off the ground, and the first 2 stages put the rocket into orbit around the Earth. Once we get into orbit around the Earth, we go about half to 3/4 of a revolution around the Earth. Then the 3rd stage lights up to send the whole spacecraft to Mars. So this whole thing is about 35 meters tall or so. So that's about 125, 130 feet. This is a photograph of the liftoff on, I forget the date, I think it was June 20th, 2003. And so one of the things that you can see you can imagine from this picture is the liftoff provides a huge amount of energy. I don't know if any of you have seen a rocket launch, but those of you that have, it's a really loud and violent event. And one of the greatest things about watching a rocket take off into space is not the sight itself. To be honest, I've seen a lot of rocket launches in my lifetime, and you know what? The view is much better on TV than it is in real life, because in real life you got to be standing like 4 miles away, and it's just this little thing in the horizon, and it goes off in the air. The really great thing is the sound. The sound is so incredible. It's this deep vibrating sound that just permeates the entire air, and it just shakes all the metal around you. I mean, you can feel this. I mean, it's like, you know, like you're trying to like fall asleep at night, and your neighbor in the dorm has their big bass stereo on. You can hear the boom, boom, boom come through the wall. But it's that those sound waves from the rocket. You can feel it just vibrate every bone in your body, and it's because it takes a lot of energy to get something off the surface of the Earth and into Earth orbit and on an escape trajectory to go away from the Earth and all the way to Mars. To give you an idea of how much energy has to come out of this rocket, at the time the 3rd stage burns out and we're on our way to Mars, this thing is moving 30 times faster than the speed of sound. So imagine, you know, when they say faster than a speeding bullet, this thing is moving 30 times faster than a speeding bullet. And it has to take, we need all that energy to escape the Earth's gravity and get all the way to Mars. So it's a really cool thing to watch it take off and go in the horizon and just disappear over the Atlantic Ocean. So there's some bad news about this, though. So all this energy stored in the rocket fuel accelerates the rocket to 30 times the speed of sound in order to get to Mars. It takes about 6 months to get to Mars from the Earth. And now here comes the bad news, is once we actually get to Mars, we're still moving pretty quick. And we got to take all that energy out in order to land. So think about all the fuel it took to accelerate this thing. It would take an equal amount of fuel to decelerate the spacecraft once it gets to Mars. And if you saw the little rover that we had sitting inside the Aeroshell, sitting on its cruise stage, let's go back a few. It's here. Look at this. This is all the fuel we carry on the little rover. So it would be practically impossible to store the amount of fuel that we would need to decelerate the spacecraft in order to get to a safe landing. So we have to rely on other means for deceleration. So when we get to Mars, we're actually, let's see here. What happens here is, all right, so we're about 30 times the speed of sound when we escape the Earth's gravity. By the time we get to Mars, we're still moving at a pretty respectable rate of about 6.1 kilometers per second. So that's every second we're moving 6 kilometers, so about 3 miles a second. So there are four primary devices in which we use to decelerate the spacecraft from the time we hit the top of the Martian atmosphere to the time we get on the ground. So since we don't have rocket fuel, we primarily rely on atmospheric drag to slow the vehicle down. Fly through the atmosphere, and we use the atmosphere to slow us down. So the first of the 4 devices that we use is actually the Aeroshell itself. So that's device number 1. And remember I said we were moving at 6.1 kilometers per second. when we hit the top of the Martian atmosphere. The problem is that when one moves that fast and you run into the air and you use the air to slow you down, well, that generates a lot of heat. And so flying through the Martian atmosphere that fast, we generate so much heat that the outside of the spacecraft will heat up to about 1,500 degrees Celsius. So that Aeroshell, you can see here, this is just an artist's rendition, is just glowing red hot. 1,500 degrees is enough to melt almost any metal that we have, or any material we have would just instantly melt at 1,500 degrees C. So that Aeroshell that we built is, some of it is made out of aluminum, some of it is made out of carbon composite. So the question here you might wonder is, well, how do we keep this thing from burning up? And we use a material on the outside of the heat shield called SLA 561V. You don't have to write that down. But what that material is, it's a material that we call, it's an ablator. An ablator is a type of material that it protects the spacecraft from the heat of reentry by the heat goes, instead of burning up the spacecraft itself, the heat will actually heat up the ablator. The ablator chars, kind of like when you're burning a piece of wood or charcoal, it chars. And once the charring starts to occur, bits of it will flake off. And as those bits flake off, it carries the heat away from the spacecraft. So that's a process that we call ablation. So basically, it cools the spacecraft by having the pieces of the ablator flake off and carry the heat away. Testing that to make sure it works is a real challenge, because trying to predict how a material will behave when exposed to a lot of heat, it's not like you're trying to predict how the motion of an object. That you can use like equations like F equals ma. It's pretty straightforward. But to predict how something is going to heat and burn up, that's really hard to do. So we have a lot of computer code that tries to predict how these ablators are going to work when they are exposed to a lot of heat. But in reality, the best that you can do is to take a piece of the material and go test it. And so this is a piece of heat shield material that we're testing in a device called the ArcJet facility. An ArcJet is a device that it's a chamber that's about the length from that wall to that wall, and it basically shoots a hot gas of xenon down the chamber, and when the xenon strikes the test object, it heats up, and it simulates the amount of heat that the spacecraft will experience when we fly through the Martian atmosphere. To give you an idea of how much heat is on this thing, it's at a heat rate of what we call 60 watts per square centimeter. So every square centimeter has 60 watts of heat put on it. That may not sound like a lot, but imagine holding 25 light bulbs in one hand. That's how much heat this thing is generating. And one of the cool things about this ArcJet is that it takes 60 megawatts of electricity to run. So our ArcJet facilities were at the NASA Ames Research Center outside of Sunnyvale, California. Every time we ran the ArcJet, we had to call the power company to tell them we were about to run the ArcJet, because if they weren't ready for it, we could take down the electricity for all the city of Sunnyvale. That's how much juice this thing takes. But I kind of have a funny story behind this. I was the chief engineer for the landing system, so I had to go around and supervise all these tests. And for this ArcJet test, this is proof positive that it's actually safe to look at eclipses. You know, they tell you, like, there was how many of you, did you guys see the eclipse the other day? Oh, what? So they tell you not to look at the eclipse because you're going to burn your eyes out. Well, I'll tell you, when I went to see this test, I showed up a little late for the test. And I walk into the facility, no one's around. But the ArcJet was there, and there was a little viewport. So I kind of put my head up to the viewport, and I was looking in, and the test occurred. I was like, wow, this is cool. And that's exactly what I saw. Then about 2 minutes later, the test was over, and I could kind of see spots in my eyes. And then they turned on the lights in the facility, and all of a sudden over the PA system, okay, test is over. Make sure you put your welding safety goggles back in the receptacle before you go to lunch. I was like, what safety goggles? So I just stared at this for 2 minutes, and I said to myself, you know what? Looking at an eclipse can't be much worse than that. So here's a proof positive that you can look into the eclipse and survive. And my eyesight's not that bad. All right. Now, flying through the Martian atmosphere, there are two challenges behind flying through the Martian atmosphere. Flying through the Martian atmosphere at high speed. The first challenge is that we all make sure that the spacecraft doesn't burn up. The second challenge is that it can't tumble end over end. The ablative material is only at the bottom of the heat shield, and if it tumbles end over end, we spiral out of control and we'll burn up. So we had to figure out, how is this thing going to fly through the air at Mars, and how is it going to maintain aerodynamic stability? So we have computer programs that run this a code called CFD. It's called computational fluid dynamics, that tries to predict the aerodynamic stability of this vehicle flying through the air. The problem is that that's all very theoretical, and that we're not sure that if this CFD code actually will predict accurately how the spacecraft is going to fly at Mars. So what we did was we built scale models of the spacecraft. This is a scale model made out of tungsten. It was about 2 inches long, and we went to this place called Ballistic Range at Eglin Air Force Base in Florida. That's a really cool place. I don't know if you remember from the Iraq War, where they had these big bombs that could just take out like football field size areas at one time. They called it the mother of all bombs. And they tested these things at Eglin Air Force Base. Well, they have a device here called the Ballistic Range. And what the Ballistic Range is, it's essentially a big gun with a diameter this big, and it shoots the test capsule down this range about 300 yards long, and it smacks into a piece of metal at the end. But as it flies down the range, we have photo stations every 50 feet that take pictures of the spacecraft of the model as it flies. And this is a picture of one of the from one of the photo stations, and we can see the wobbling as it flies down the range. And by measuring the wobbling in the photographs, we can reverse derive the aerodynamic coefficients of the vehicle. But the cool thing about this range is that it's loud. When that gun fires, it's like a big ship's cannon going off. Now this photograph was taken on September 11th, 2001. Now you all know about September 11th. We were in the hotel that morning when we had heard that the World Trade Center had been hit by airplanes, and I was just thinking to myself, because just in disbelief, like we hadn't seen, no one had ever heard of anything like that happening. So I said, okay, that's just some minor news story, and we're going to go off and do our test. Well, that was a really poor decision, because I can tell you when we went to push the button to light off that cannon, huge boom, and the whole building shook. I'd never done this before, and it actually sounded like the base was under attack. And then the next thing you know, about 5 minutes later, phone's ringing. It's the colonel from the base commander's office. Like, what the hell are you guys doing out there? Everybody's thinking the base is under attack, so they shut us down for the day. So that was just kind of an interesting story. But they invited us back a month later, and we actually finished this test. So now, turns out it takes more than the Aeroshell to get us down to the surface. The Mars atmosphere, even though we use the Mars atmosphere for deceleration of the Aeroshell, the Mars atmosphere is still really thin. In fact, the density of the Mars atmosphere is only 1% of what we have here on Earth. So even if we allowed the Aeroshell to decelerate us, we would still hit the ground supersonically. Aeroshell was not enough. And so this is device number 2 that we used, was a big parachute. So once we got to about an altitude of, I'm going to say, I think it was about 7 or 8 kilometers above the ground, we had to deploy this parachute. But at that point, we're still moving at twice the speed of sound, and the forces on a parachute at twice the speed of sound are huge. And so we had to actually test the parachute to make sure that it would survive the forces of inflation. And so the way that we did that was that we went out to this test range near the Boise Airport in Idaho called the Orchard Proving Grounds, and we dropped the parachute on the back of this big missile. And this big missile weighed about 10,000 pounds, and the idea was to accelerate the parachute to such a speed that it would the parachute would experience a lot of force equivalent to what we would see on Mars for a Mach 2 or twice the speed of sound inflation. And I remember when we were designing that little missile, the guys designing it warned us. They said, you better watch out, because if your parachute fails and that missile falls to the ground in free fall, it's so aerodynamically slender, it'll generate so much speed that it'll break the sound barrier going down and hitting the ground. Well, so let's see if I can play this video. Whoops. Let's see, how do we play? I think we just click. So here you can see we have a camera. We're on the camera is on the top of the missile. And you can see the parachute flying up, being deployed. And then the parachute's inflating, 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 inflating. And then poof, parachute ripped itself to shreds. And so I don't know if the thing broke the sound barrier hitting the ground, but I can tell you we had to get out our shovels. It took us 8 hours to dig the thing out of the ground. So there we were thinking, okay, well that wasn't expected. But and we also had here's another funny story. We also had another problem in that when we examined the test, even though the parachute got shredded, we realized that we didn't generate enough speed. So we shredded ourselves on a test where the test itself failed because we didn't generate enough speed to generate the right forces. So we were at the hotel that night, and everybody was kind of in a down mood. And we were trying to figure out, well, how can we generate the right amount of speed to test the parachute? And somebody, one of my team members suggested, okay, well, why don't we use a locomotive, meaning that they wanted to have a locomotive go down a track at 70 miles an hour, deploy the parachute, and the locomotive would keep pulling the parachute to generate the force, the right aerodynamic force in the parachute. Well, I didn't know that's what he meant. I thought he wanted to use a locomotive, drop the locomotive out of the helicopter, and tie the parachute to the end of the locomotive. And so this is how desperate we were. I thought to myself, all right, well, the locomotive would weigh enough. Then I thought to myself, how much would a locomotive cost? I figured, I bet you a locomotive, I'm not in the railroad industry, but I thought, all right, maybe a locomotive might cost $250,000. That's, I could imagine, $250,000 to buy a locomotive. And that's how crazy things got. And I said, I think I could talk my boss into $250,000 for a locomotive. But that's not, that's not what they meant. So ultimately, in order to test the parachute and to have the wind be at the right speed for the test, we went to the world's biggest wind tunnel in Moffett Field, California, at the Ames Research Center. So this is the device we used to prove to ourselves that the parachute could actually withstand the forces of inflation. It really took us 2 years to figure out how to sew the parachute correctly, such that it wouldn't shred to pieces when being deployed at Mars. This facility is huge. I mean, imagine like standing inside a sports arena, and that's how big the cross section of the wind tunnel was. Now we had another problem here, which I'll show you. So this is a picture of us trying to inflate the parachute in the wind tunnel for the first time. There's a video here. So you can see the parachute being inflated, and look at that. It's not really inflating. It's kind of just sitting there, kind of like in this jellyfish-like motion, and it never inflates. And this is a phenomenon that we call squidding. So we had several problems here. Not only was the parachute shredding to pieces, but we didn't design the parachute right so that it would open correctly at Mars. And this really, it took us 2 years to solve the problem of how to get the parachute from shredding itself to pieces on inflation and how to get it to stop squidding. And this is one of these things where the parachute, it's not like, as I said, there's no equation that you can write to describe how a parachute is going to open. You basically have to go through trial and error. I mean, it's hard to write an equation to describe how cloth moves or how cloth is going to behave. And so it's literally just trial and error, trial and error, trial and error. And it took us 2 years to get this right. The solution, it turns out, we're running out of time here, but the solution to the threading, the stitching, was that we had to reinforce the stitching along the bottom of the seams. And it was the fact that we could test in the wind tunnel that allowed us to figure this out, because when we were testing by dropping out of a helicopter, we couldn't tell the video resolution, we didn't have HD TV in those days. The video resolution wasn't good enough for us to tell where this thing was shredding. But with the wind tunnel, we could inflate the parachute, and even though the wind would be blowing at like 60 miles an hour, we could be in the wind tunnel looking at the parachute and looking for the stress points on the parachute, and we could actually see them, and that's where we figured out where we had to reinforce the stitching on the parachute. Okay. So the parachute was device number 2. The third device that we used to slow down the spacecraft to a gentle landing were these retro rockets. And the retro rockets, the reason we had to have the retro rockets is, remember we said, all right, with the Aeroshell, we didn't have the parachute, we would slam into the ground supersonically. Well, on Mars, it turns out that the air is so thin that even with the parachute is not enough to slow us down to a safe landing. So to give you an idea, there's this concept that we call that people jumping out of airplanes, which is not a smart thing to do, but it's called terminal velocity. Terminal velocity is if you jump out of an airplane and either with a parachute or without a parachute, there will be a speed at which you will accelerate to and you will fall no faster. So on Earth, if you jump out of an airplane without a parachute, your terminal velocity is going to be 120 miles an hour. You will hit the ground at 120 miles an hour. On Mars, with a parachute, our terminal velocity was 195 miles an hour. So on Mars, terminal velocity is higher than jumping out of an airplane on Earth without a parachute, just because the air is so thin. So that's why we had to use the retro rockets to slow us down. And so here is a photograph of a retro rocket test that we had, that we did out in the desert. So you can see we had 3 rockets that we used to slow us down. Now the retro rockets themselves were actually adequate enough to slow us down to a safe landing, but the problem is that these rockets aren't very accurate. There's a lot of errors in terms of like how much thrust we're going to get out of the rockets. And we also had a flight computer on board in which we had to ignite the retro rockets at the proper altitude. And if we were a little off in the calculations, well, we wouldn't hit the ground. We would hit the ground moving not at the speed that we would like. So we had to employ device number 4 to slow us down, which was these things called airbags. And the airbags surrounded the lander, and it's essentially as you think they are on Earth. The airbags cushion the collision of the spacecraft with the ground. So to give you an idea, these airbags are made out of Kevlar. Those of you that know, we make bulletproof vests out of Kevlar. And the reason for that is that Mars is filled with lots of sharp, jagged rocks. If you've ever been to the big island of Hawaii, there are lots of rocks on the surface, and you try to run your hands on them, you cut yourself. Well, Mars has all sorts of jagged rocks like that. And so these airbags actually are multiple layers of Kevlar in order not to get punctured. And you know, we think about spaceflight and as being very high-tech. Well, sometimes it takes very low-tech things to make the space program work. And so this is at our facility in New Jersey, actually it's in Delaware, where the airbags were manufactured. And you can literally see here that for all the sophisticated technology that we put into the airbags, the success of the mission hinges on the fact that there are seamstresses that can sew the airbags properly. And it's their handiwork counts more than any of the equations that we can put into solving the problems. What's really neat about the airbags is that the women that sewed the airbags, they were trained by the same woman that sewed Neil Armstrong's spacesuit for Apollo 11. So sometimes, you know, you can think of all the sophisticated equations, computers that we have. It really comes down to handiwork that makes the space program work. And they use sewing machines, actually. These are 1930s vintage sewing machines. And the reason that they have to use these ancient sewing machines is the sewing machines that you have today, they're very fragile. And these sewing machines have to sew Kevlar. And so they don't make these things anymore. So they actually had to scour the country for sewing machines that were made in the 1930s to do this job. So how do we test the airbags? The airbags were hoisted on, we have a 300-foot vacuum chamber in Sandusky, Ohio, by the Cedar Point Amusement Park. and we hoisted it up to the top of this vacuum chamber, pumped out all the air, and we had this ramp full of jagged rocks, and we would repeatedly drop the airbags on this ramp full of rocks to test to see if it would work. And these are photos that we took. And so what happens is the airbags will hit the rocks, and then each rock had a different colored chalk on it, and it would tear the airbag apart. And based on the color of the chalk that we saw in the airbags, we knew which rock damaged the airbags, and we could look at the shape of the rock, we could look at the type of tear, and we could make guesses as to how to resew the airbags to make them more robust. Each one of these tests took 2 days to do in terms of pumping down the chamber, hoisting the airbags to the top, and then resewing the airbags so that they could survive another test. We had to run 55 of these tests over 2 years to get the airbags to work. So spent a lot of time in Sandusky, Ohio. So anyway, there's probably a lot more we could talk about here, but you know what? I'm going to show you the first part of a video that kind of puts this all together, give you a little bit of the excitement. I'll stop it at 3:20, since I know you probably want to head off to your next class. So we can watch the first 4 minutes of this here. Window. How do we go full screen on this? I think it's the, there we go. There we go. It's a government thing. Don't worry.
T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, ignition, and liftoff of the Delta II rocket with Mars exploration rover.
right, so anyway, I'll pause this here since the class is just about over. But one of the things I wanted to mention in closing is that sometimes you got to leave yourself a little margin for error. When we dropped the airbags on the ground, we were supposed to be 45 feet above the ground. The airbags were going to cushion the impact from 45 feet above the ground, and that was to allow for error in the rocket firing time. Well, we got the data back that night, and it turns out we were only 18 feet above the ground when the rockets fired. And so I remember driving home that night, and I live in a 2-story house, and I kind of looked up, and I was like, wow, 18 feet is less than the height of my second story. And I thought, you know what, man, we went like 60 million miles from the Earth to Mars, and we only cut it with 18 feet to spare. I was thinking, boy, I was cutting it a little close. So this kind of a little lesson here that when you work on things that are this expensive, that leave yourself a little margin of error. So anyway, I'll be around for a few minutes if you have any questions. Sorry to run late.